Something strange happens when you put two vortices right next to each other. And it explains what happens to the vortices behind an aircraft, to two vortex rings that are shot at each other, and even explains the behavior of a gas cloud around a supernova. Today we'll discuss. Before we go any further, we need to understand what a vortex is. A vortex is essentially a bunch of fluid particles rotating around an axis, traveling in a helical path, somewhat like this. Now, the particles in a vortex are lightly bound to this low pressure core, which means that you can't think of a vortex simply as a discrete collection of particles. You have to think of it as an entity, as something with a bit of continuity, which means think of this rope as a vortex. This piece of string is a vortex. Now, if I apply some force on a random section of this vortex, let's say here, I push it upward, you'll see that the upstream and the downstream sections have deflected to maintain contact with this deflected part. This deflected part did not just cut off independent of these two sections. They followed to maintain contact with it. And this is very similar to how vortices actually behave in real life. They behave much like a rope. Now, since the vortex is made up of particles that have mass and they have velocity now, they have momentum. And if they have momentum, they can impart forces on particles lying close to the vortex. All the surrounding air molecules, they can get hit by the particles of this vortex. Now this brings up a very interesting possibility. Let's put another vortex close to this one. Let's say vortex B, and the first one will be vortex A. Now A can induce a force on B and B can induce a force on A. This is called mutual induction. Now let's take another vortex, a single vortex this time, A, but this time the vortex is curved. This is a very poor rendition. Okay, this part of A can induce a force on this part of A. This happens within the same vortex, and that is called self-induction. You'll see that many of these terms are borrowed from electronics and magnetism, which is going to be a common theme in this whole explanation. Another thing you have to understand before we start getting into the meat is vorticity. The vorticity vector of a vortex is pretty easy to understand. Let's imagine you're looking at the cross section of a vortex. So vortex is like this. It is spinning in this direction. To find the vorticity vector, all you have to do is to follow the right hand rule. Curl your fingers in the direction of the vortex, in the spin of the vortex, and your thumb will point in the direction of the vorticity vector. In this case, the vorticity vector is pointing out of the page in the positive y direction. Let's take the example of an aircraft in cruise to explain Crow instability. When you look at an aircraft flying overhead, you'll see these two white trailing lines behind the aircraft. Now those are two huge vortices behind each wing. For our example, we are going to look at the aircraft top down, which means that this is the suction surface of the wing, or the low pressure surface. You'll see on a closer look that vortices are actually being generated at every point along the trailing edge of the wing. And these vortices form a vortex sheet, a 2D sheet of vortices that eventually roll up some distance behind the aircraft to form that final vortex that you see from the ground. Looking at all these vortices that make up the final vortex, the one at the tip is the strongest one, and that is for a very good reason. The tip is a discontinuity. There is nothing beyond it. There is nothing stopping the high pressure air at the bottom of the wing from flowing around the wingtip to the top to meet the low pressure air, unless we have wingtip devices, which we are going to discount here. And that leakage of air will cause a very strong vortex to form behind the wingtip. The position of this final vortex is the positional average of all these tiny vortices combined. And since the one at the wingtip is the strongest, that the tip vortex will mostly determine the position of this final vortex. It has most of the say in where the final vortex will form. Now, what determines the strength of this tip vortex? That is determined by the lift distribution curve. Now, this graph basically tells you how much lift is made and where it is made on the wing. You'll see that in scenario A, a ton of lift is still being made at the wingtip. That means the pressure differential between the top and the bottom of the wing at close to the tip is going to be very high, and therefore that positive pressure gradient is also going to be very high, and therefore the tip vortex will be strong, and it will have more of a say in where the final vortex forms. Therefore it will pull the final vortex close to the tip, outboard. Now let's look at scenario B. In B, you'll see that not a lot of lift is being generated at the wingtip. Therefore, the wingtip vortex is going to be weaker. It will have less of a say in the position of the final vortex, and the final vortex will move inboard, closer to the root. Now, what causes changes in lift distribution? I know I'm going on a sort of a rabbit hole here, but all this will make sense, I promise. Okay. The changes in lift distribution are mostly brought about by angle of attack, by changes in your wing plan form, basically how wide and how thick or how long your wing is. Now, angle of attack will change throughout your flight. You may not realize it, but the free stream that the aircraft is flying through is not uniform. It has updrafts, it has downdrafts, it has gusts, and all these things you'll sometimes feel as turbulence in your when you're sitting in an aircraft. Now those things affect your angle of attack slightly, but it will still affect the angle of attack. Or sometimes pilot input. Let's say the pilot input causes actuation of your ailerons or your spoilers or your flaps, and those things will change your lift distribution. Or sometimes newer aircraft, they have active turbulence mitigation and flutter control, and all those things will constantly change, slightly but constantly change your lift distribution curve. Now imagine a scenario where your lift distribution curve is going to change from A to B and fluctuating between these two states. Now obviously the difference here is exaggerated, but for our purposes, let's imagine. Now what that will cause is your final vortex to move inboard and outboard constantly, to basically fluctuate. Now, the fluctuation of the position of the final vortex will create these curves in the vortex that is shed downstream. That is because we've already established that a vortex has continuity. It behaves much like a rope. When the final vortex moves inboard and outboard, it is still connected to the vortex that was shed in the downstream, and therefore you get these curves. Obviously here we have limited our cases to where the lift distribution varies across both wings equally or symmetrically, and therefore you get this symmetrical pattern where at some points both the vortices from both wings come closer to each other, and at other points they are farther apart. So let's call these points as nodes and these points as antinodes. Something else we have to understand before we go a little bit advanced is how mutual induction works in a practical sense. So you're looking at the cross section of both these vortices A and B. Now to figure out how A is going to induce a force on B in which direction, just imagine a particle of A that's going around and just increase the diameter of the path till your particle intersects with the core of vortex B. So you'll see that the particle is going to hit B, essentially going around like this till it hits B like that, and therefore vortex B is going to be pushed in this direction. Similarly, vortex A is going to be pushed by B in this direction. So I've made some props here out of wire because we're going to get into the 3D explanation of Crow instability, and it is going to be much easier to do this than to do it all on paper. So first we come to this. This is essentially where we left off the explanation on paper. You can see that this is the direction of flight. The aircraft is moving in this direction. We'll call it positive X, positive Z, negative Z, positive Y, and negative Y. Negative Y is pointing in the direction of the Earth towards the ground. To establish the vorticities now, any vorticity in this plane is axial vorticity. Anything in this plane is a radial vorticity. Anything in this plane is azimuthal vorticity. Okay. Now, let's name these vortices. Let's name this A. Let's name this B. You can clearly see the nodes and you can see the antinodes. Okay. So at the nodes, obviously, the vortices are closer together. They are going to experience more mutual induction than at the antinodes. Looking at the spin of the vortices, B is spinning that way, A is spinning this way. Therefore, both of them will induce a force on each other, trying to move the vortices, trying to push each other in the negative Y direction. So they're both trying to push each other towards the ground. Now obviously at the nodes they're going to push each other harder than at the antinodes, which is when you end up with something that looks like this. So here you can clearly see that this force has obviously caused the nodes to push each other towards the ground further than the antinodes because of the difference in mutual induction, in the magnitude of mutual induction. So now you've got these troughs and crests along with the nodes and the antinodes we've talked about. Those troughs and crests have now introduced radial vorticity into this whole mixture. So now you got some radial vorticity. It's not yet significant enough to cause physical effects in the vortex, any induction or mutual induction, but it is still developing and it will eventually get there. You leave this for a few seconds to develop and you get something that looks like this. Now this is a very transient stage of Crow instability. That is because if you look at the nodes, you'll see that now there is significant radial vorticity happening at the nodes. There is a very marked trough and you get a bunch of new forces that you have to deal with now. So first, the first new force you get is the self-induction between these two segments of B and these two segments of A. So let's look at the spin again. This segment is spinning this way, this segment is spinning this way. Therefore, both of them are going to push the trough towards the other trough, trying to hit the other trough. Similarly, this vortex A is also going to do the same thing. But these vortices, they are not exactly parallel lines. They are V-shaped. So the self-induction between these two sections at here is going to be much higher than the self-induction here because they're farther apart. So instead of just moving towards each other, what you get is this twisting motion. This twist happens. They twist into each other. What happens when they twist into each other? The mutual induction between these two parts, the first force we talked about, it shoots up because of the inverse square law. And when that shoots up, you get movement, further movement in the negative Y direction. Now what happens if there is further movement in the negative Y direction? Well, these segments become more vertical. They start to become more vertical. Now what happens if they move vertical? There is more radial vorticity. And the self-induction vector, which was pointing like this before, is going to start to point like this, which means that self-induction just became more effective, more efficient in bringing these two sections together. Therefore, you get more mutual inductance, and therefore more movement in the negative Y direction. So you see where this is going. This is going into a positive feedback loop, a runaway situation, but obviously it's not infinite. It ends with
vortex A and vortex B colliding with each other at this node. Before we go there, however, there is another force we've not talked about, and that is the mutual induction between A and B, these segments of A and B. Looking at the spin, you can see that B is spinning this way, A is spinning the other way, and therefore this force is actually trying to pull these nodes apart. We don't consider this force to be significant because of the extreme distance between these two segments. So this force does not have any physical manifestations as of now in the development of the Crow instability. But once the vortices collide at this point, let's say the vortices have collided here, so you have to imagine that these vortices are actually spinning in opposite directions. So you can imagine the particles of one vortex going one way, crashing into the particles of the other vortex going the other way. So you get a bunch of turbulence here. Essentially, the point where these vortices collide actually cancels the vortex because of the crashing of particles, and it just devolves into a bunch of turbulence. These two sections, it devolves into a bunch of turbulence. So what happens then? Well, this section of A loses contact with this section of A. Same happens with B. So you get open ends or cut ends of vortices, precisely 4 cut ends of vortices here. The properties of a vortex tell you that a vortex cannot exist open-ended within the same fluid medium for a prolonged period of time. Now let's reevaluate our forces. The self-induction between these two parts and these two parts is still active, trying to push these two sections together. The weak mutual induction between these two sections and these two sections is also still active, trying to pull this node apart. And you've got the 4 cut ends of vortices somewhere in here. So now something very interesting called Vortex Reconnection happens. Because of the forces, the one trying to bring the segments together and the one trying to pull them apart in the axial direction. Now those forces and the proximity of the cut ends of the segments actually cause something like this, where it is much easier for this cut end of vortex B to splice together with this cut end of vortex A, rather than to travel the extra distance to reconnect with its own cut end. So what you get is crossing of vortices, cross splicing of vortices, if you may. Now you might say, well, those vortices are spinning in opposite directions. How is B possibly going to splice with A without cancelling itself, like we saw at the nodes? Well, that is because we are operating in the third dimension here. Once B splices with A or vice versa, you can actually follow the vorticity vector using this pencil all around the newly spliced vortex in the shape of a ring continuously. That means you've got a vortex ring. In fact, you get a bunch of vortex rings in the wake of an aircraft, and these vortex rings will persist in the air for some time, and eventually they dissipate by friction.
When Destin put out this video of the vortex rings colliding, there was no mechanism provided for how the secondary vortices would form. There were a few hypotheses, but nothing solid. But I think Crow instability can explain what we are seeing here. For that, we just have to modify our initial starting conditions a little bit. In our example, we took 2 linear vortices. Instead, take 2 circular vortices or vortex rings and put them adjacent to each other, parallel. Then you apply all the forces we went through in our explanation, and then you'll see that you get exactly what you see on screen. And I think the biggest tell here is this. The secondary vortices are half red and half blue, and that too on the respective sides of where the initial vortex came from. And that can only happen if those vortices splice together, or that vortex reconnection, which we talked about in the last part of the explanation, was happening.
And I think that pretty much tells you that this is a special case of Crow instability. This is Supernova 1987A, and it is about 163,000 light years away from Earth. When you look at it, you see this glowing ring of gas. But when you look closer, you can see that there are evenly spaced clumps of hot glowing gas embedded into this ring, giving it this string of pearls-like appearance. The best explanation we have for it is actually Crow instability. It is said that the blue giant star that once occupied the space that the supernova now does had an annular ring of hydrogen gas wrapping around its equator. And over time, the stellar wind emanating from this blue giant caused the top and the bottom edges of this annular gas cloud to curl away from the star and into itself, forming two vortices rotating in opposite directions wrapped around the star. Over time, these vortices interacted, undergoing Crow instability and forming secondary vortices that we see as clumps of hot glowing gas through our telescopes on Earth. So that's all I have to say about Crow instability. I know there are probably a bunch of errors in this video. That's because I don't have a formal education in any of these topics, unfortunately. So I'd love for you guys to correct me. Please write to me in the comment section or send me an email, and I guess I'll see you in the next one.